Hello everyone, and thank you for joining us for today's online workshop. The title of today's session is Application of Sorption Science in Food Research, and this session has been organised in partnership between Surface Measurement Systems and Hochschule Bremerhaven. Before we proceed with the presentations today, I'd just like to remind everyone a few house rules and how you can all take part in today's workshop. We'd like to remind everyone to please keep their microphones mute for the duration of the presentations so that we don't get any feedback or background noise interrupting with anyone's listening experience. And for those of you who would like to engage in the live Q&As at the end of each presentation, you can do this in two ways. You can submit your question in writing in the questions tab, which you can see in the webinar control panel. And then the host, who is myself, will ask the speaker your question directly at the end of the presentation. Or alternatively, if you would like to unmute your microphone and ask the question to the speaker directly, you can simply raise your hand at the end of the presentation and the host will let you know when you can unmute your microphone. So once again, if you would like to ask a question of the presenter, please submit it in writing to the questions tab or raise your hand at the end of the presentation and we will let you know when you can unmute your microphone. To kick us off today, we are very happy and very humbled to have Professor Dr. Edgar Langenberg, a professor from the Institute for Food Technology and Process Engineering from Hochschule Bremerhaven. We're really thankful to Edgar for taking the time to be with us today and for helping us coordinate and produce this online workshop. So without further ado, I will hand over to you, Edgar.
Okay, thank you for your kind introduction and thank you for the partnership and setting up this workshop. So from our point of view in the field of food technology and process engineering, we are just looking for powders, part of powders, and always the same question is it still flowing or is it already sticking? That's our main focus in our research, and probably we are just having different types of powders, so some blue, green or whatever, some big and the other one not so big. And the main reason if you are looking to powders is something like this here. So we are looking in the case of particle size, of thermal analysis, so what is about the glass transition temperature, so is the texture, and how is the behavior in process like in freeze drying or fluidized bed or spray drying, and also in milling process, or what happens with the particle form, and all this stuff is the main focus we are looking for to figure out if this powder is quite useful for us or if it makes a big problem sometimes in process. So if we are running in process, we have just one focus. One focus will be the fluidized bed. So we have just coating process or agglomeration processes, which can be very good and very straightforward, or which could be a disaster depending depending on the powder and depending on your parameters. So in any case, you can use it as just as a coating process, or you can use it as a drying, or in some other cases, some guys use it as a mixing bed. And on the other hand, we are looking for is behavior just in spray drying. So what's happened, we have a suspension or whatever, a pump, and just making a spray and drying it in a very short time. So the contact time with the heat is very short, and you will get hopefully some good powders, but in some cases you won't get a good powder. You will get something like this here, caking of powders, and that's also a big issue, and we would like to figure out why some powders are caking and the other things don't. And if you are looking in the literature, and you will find that caking is also a problem in different parameters. So our short talk will be just have a flashlight to the amorphous caking and the glass transition temperature. And if we will see later probably there is humidity caking, and you will also see the mechanical caking, and everything interferes with everything. So that's the main big problem in this field. You can see the humidity, the temperature, the water activity, water content, and all the parameters have an influence on the amorphous caking and on the glass transition. And one of our main focus is to figure out what's happened with the structure. Is it just crystalline, or is it an amorphous structure, or is it something in between? And as you already know, I think we won't get any melting without the crystals, but some powders, some crystal stuff behave like this one here. You can heat it up and you will see just a wonderful melt. And on the other hand, you are just doing a cooling. You won't see any recrystallization in this field. You will just see a glass transition. And on the second heat, you will find also only a glass transition. And there will be no crystallize in this field. So the reason or the parameters why, that's the main question we have. And one big issue is also the glass transition temperature. So if we are just have a short look to the glass transition, otherwise I think we are running out of time, we will find that the system always have two ways to answer. So if we are starting from the melt and starting with the cooling, you are just have two ways. Otherwise, it would be the right or the wrong way. You cannot say what's the right or the wrong way. So you will see here, it could be just a really good fine crystallization. And on the other hand, same from the melt, you will go to a glassy state or in the glass transition. And it's up to you and up to the powder what's happened on this case. So sometimes we go direct in the crystallization, and on the other hand, if your parameters are wrong or the water activity is too high, you will go in this field of glass transition with all the difference we will see in the next couple of slides and in the next few minutes. One thing what could happen is if you just see here the storage modulus over temperature, you will find water as a plasticizer. So it could be the stiffness of all this powder will be decreased very strong, and you see that's the log scale here. So the stiffness of the powder with a content of MART1 is very strong, but the stiffness in this field is very weak. So the glass transition starts a few degrees earlier than on the other hand. And that's one part. So the interaction between water and the glass transition is one of the biggest issues. On the other hand, there is a second issue, which you have to figure out quite easily. That's the frequency response of the powder or of your structure. And you see the frequency has a big influence like the temperature or like the water activity. So if you have a mill and you will treat your powder with a high or with a low frequency, you see with a low frequency, it will be in a glass below 110 degrees. So if you treat it with a high frequency, it will be in the glass above 140 degrees. So what's happened during transportation? How is the frequency load of the transportation? That could be also one of the biggest issue which you would like to figure out. And on the other hand, as you already know, we see that in case of amorphous sucrose and a heating run, we will see that there is difference in the water activity, and the water activity shifts the glass transition and also initialize the cold crystallization earlier than in this field where the water activity is very low. So that's the main reason why a powder can cake or a powder will be suitable and flowable. So that's one of our focus to see what's the behavior of the powder, and we have several processes where it's always an influence of the water and on the temperature and on the behavior of the glass transition temperature belonging to the water and to the field of temperature. And if you are looking for agglomeration, on the other hand, you are just looking for stickiness and caking. So you would like to have caking and stickiness, but on the other hand, if you're adding too much of the liquid, you will be in the collapsed area and you won't get any agglomeration. And if you are just too far away from the caking area, you will get in the glass and in the glassy state. So the tech will be reduced quite tremendous. And that's also an influence you have to take aware. And that's the reason why we are looking in this field, what's happened if you changing the water or what's happening with the temperature, in this case of the TG. And one big issue in the food, also spray drying. So if we are looking forward, what's happened in this short contact time from the fluid with the small particles. So you will dry it and you have to pass the sticky zone, and then you have to be in the glassy state. Otherwise, you will get a caking scenario. And but also you will see from many cases we see that it won't work only with a substance, and that's a little literature here. So if you're using spray drying for honey without maltodextrin, you cannot dry it anymore. So you are running out on this problem. So you will find a tacky, viscose badge of your tower, and you cannot use it anymore. But you have to find the right maltodextrin and the right parameters to get in this glassy area. And that's things we can do with some tests in the spray drying system. And we are looking for glass transitions in this field of dynamic scanning calorimetry. But we will see that there are also different possibilities in the things of sorption and desorption. But anyway, if we are having problems with caking, from time to time, you will see that it's also the mechanical power which can get in this problem. On the other hand, you will see, okay, the main problem is where you pass the TG or not. So if you have a plastified surface, a tacky surface, and then it sticks all together, or if you are under the critical temperature or under the critical water activity. But if you're in this area here or close to this area, you can figure out that something happens here in this case. So if you are looking to the bag here or at the top, you will find there is a lot of pressure on the bag on the bottom. And what's happened if the condition is not right? So if you're in summer and the humidity getting higher, then you can running in this serious problem. Over time, you will get a caking process, and all the powders will get a big block, and then you are running in serious problems. So that is just a short introduction in this field where we are working in, and that's some wonderful pictures from the university in Bremerhaven and on the seaside of Bremerhaven. So thanks a lot for this, for your time and the short introduction. And I hope we will get a little bit more wonderful information about the sorption and desorption. Thanks a lot. Bye-bye.
It doesn't look like we have any questions for now. For anyone, if you do have questions for Professor Langenberg, please submit them in the questions panel, and we can ask him at the Q&A session after the next presentation. So our next presentation will be delivered by Meishan Gao, an application engineer at Surface Measurement Systems. Meishan joined in 2018 and has since then worked on surface characterization of solid materials, including fibers, powders, and film samples, using dynamic vapor sorption and inverse gas chromatography as the main techniques. Meishan obtained her master's degree in chemical engineering at Imperial College London in December 2017. Her research project was focused on investigating the properties of fragrance molecules with solid substrates by diffusion and sorption. She also received her bachelor's degree in chemical technology at the Hong Kong Polytechnic University and in chemistry at Sun Yat-sen University in June 2016. So without further ado, I will hand over to Meishan to give her presentation.
Thank you, John. I'm sharing my screen now, so I hope you can see it.
Yes, we can see and hear you, Meishan.
That's great. So hello everyone, I'm Meishan, and thank you very much for joining today's workshop. So in my first talk here, it will about the application of the sorption science in the food research, and we are using the dynamic vapor sorption in this presentation. So here's the outline of the presentation. I will first give a brief introduction about the DVS technique, and then we can go in details about different kind of applications, just giving you an idea about what's the capability of the DVS measurement that could be useful in the food research. So moisture is everywhere in the real world, and the relative humidity can vary in different regions. The interaction of the moisture with the solid material will have a great impact over a wide range of industries, including like pharmaceutical, foods, proteins, or some other personal care products. And especially in the food industries, moisture will cause lots of different problems. For example, powder caking that will affect the powder flavourability, or the instability of the material, both physically or chemically. And moisture can also induce the phase change, for example, dissolution or deliquescing of sugar at higher humidity environment. So it's very important to study the moisture sorption behavior for the prediction of the shelf life or the stability of the food components. And DVS here can be a very useful tool to study this kind of moisture sorption behavior. So DVS is short for dynamic vapor sorption, which is basically a gravimetric method to measure the change of mass for the sample at different concentrations of moisture or organic vapor. So in the system, we will have a macro balance like this one, which have a resolution of 0.1 microgram. In that case, we just need to use very small amount of sample for the analysis, and typically just around 10 to 20 milligram, depending on the uptake of the sample. And as a dynamic system, we will have a continuous flow of the probe molecule to the sample constantly, so we can achieve a much faster equilibrium compared to the sorption systems, the static sorption systems. And we can perform the experiment both at ambient temperature pressure, as well as we also have a system can perform the experiment at vacuum pressure as well. And the ambient pressure is very important, especially for some sensitive or fragile material that we can keep the hydration water during the measurement compared to some other method like nitrogen sorption that will expose to the extreme condition like vacuum that will lose the hydration water. So here's an example with one of our system, which is the DVS resolution, can perform the sorption of both water and organic vapor, as well as it can generate two components at the same time and doing the co-sorption or the competitive sorption of two different components. So the principle for the experiment, in the middle here, we have the macro balance with the resolution of 0.1 microgram. Is connected to both the sample pan and the reference pan. The carrier gas for the system could be nitrogen or dry air. And we have two different bottles at the back as the reservoirs, One is for the water, and the other side is for the organic vapors. So the mass flow controllers inside the system will control the flow of the carrier gas and the saturated vapor in ratio to reach a certain level of relative humidity or partial pressure. And the sensor at the beginning here will detect the concentration of this mixture and see whether the concentration is matching with the actual generation is matching with the target value. And this mixture will flow to both the sample chamber and the reference chamber at a constant rate. And the sample inside the chamber here will pick up the moisture, and the mass change will be recorded by the balance. And the whole stand for the DVS system will be set in an incubator like this one with the temperature range from 5 to 85 degrees. That means we can perform the experiment with a very wide temperature range from 5 to 85 degrees, still with very good generation of the concentration or relative humidity. And under the sample chamber like this one, this location, we can also install a preheater that allows to preconditioning the sample before the experiment in situ up to 200 degrees. And the DVS system can also be integrated with some other spectroscopy method like Raman or NIR method. And we can also install a video at the same location here as the preheater that allows you to taking the spectra or the photo images at the same time running the DVS experiment. So for example, the DVS integrated with video function, we took some photo images for the sugar sample when we ran in the DVS experiment. And you can see at dry condition is a kind of, the sugar sample is a kind of powder form. And then it goes through the glass transition at around 30% RH, and then crystallization, and finally deliquescence at the higher humidity levels. Another example was the freeze drying material. So you can see at a certain point of humidity, the sample will just shrink and then go to the liquid form. So with the video function, it's a very useful tool to compare how the sample is changing in the nature, like changing to different color or changing to different form, along with the DVS experiment. The same DVS can also be integrated with Raman or NIR spectroscopy method that we can take the spectra at the end of each humidity step. So here's an example with the amorphous lactose sample at 25 degrees. On the left-hand side is the DVS data we will get, which is the mass plot. So the blue line is the target partial pressure of each step. We're increasing the humidity from 0% RH to 90% RH with 10% intervals. The right line is for change of mass for the sample. So you can see at each percentage RH, the sample is picking up the moisture, it's reaching a perfect equilibrium, and then jump to the next stage automatically. And something happened at 60% RH this step, you can see a significant decrease in the mass, which is due to the amorphous to the crystalline phase change. And this phase change doesn't show the same in the second cycle. So this is a kind of irreversible phase change happening in this case. And from the Raman data on the right-hand side here, which is taken at the end of each humidity step when it's reaching equilibrium, and we can see at 0 and 40% RH, it has a very broad peaks, which showing an amorphous phase. And exactly above 60% RH, there are some new peaks showing up here, which is just indicating of the crystalline phase change. So this Raman data just confirming with our observation in the DVS data that at 60% RH, the sample will go through the amorphous to the crystalline phase change. And the combination of the Raman and the DVS data, along with the video images, at the same time, we can get lots of different information about the solid characterization of some kind of solid material. And that's just the basic introduction about the DVS system. Then we can go some different applications. We can use DVS system to do lots of different kind of measurements for different physical parameters. And here are just some of the applications that might be relevant in the food research. So the first one, with the DVS method, we can perform a very typical method, which is the step method, that we increase the humidity step by step as we introduced previously. So here the blue line for target partial pressure, and this time we're changing the humidity from 0 to 90% RH, going back to 0 and the second cycle at the same time. And the right line is for the change of mass for the sample. So the sample is picking up the moisture, reaching a very perfect equilibrium, jump to the next stage. And these are the 2-cycle experiments. And the second cycle here just exactly the same as the first cycle. So the uptake is the same, and it's going back to 0 at the end of last desorption step. That means this kind of moisture sorption for the rice starch sample is a perfectly reversible process that all the water can come out of the sample and then go back to the same level at the second cycle as here as well. And the first step, just the losing mass of the rice starch sample, which just the flow of the carrier gas to the sample, can also starting the drying behavior of the sample, which is by removing the freely bound water on the surface of the material. And this is just the mass plot giving some kind of kinetics information for this kind of moisture sorption. And if we are taking the mass at equilibrium state at each percentage RH, and plotting against the relative humidity, then we can get this kind of isotherm for the moisture sorption with both sorption and desorption branches. So some kind of information we can get from this water isotherm, for example, at 90% RH, this kind of sample can pick up around 20% change in the mass, which means the sample has very good affinity with water. And those water molecules are not only on the surface of the material, but also penetrating surface and then go to the bulk of the material. And that's also the reason why you see the desorption, there is a gap between the sorption and desorption, which is called the hysteresis gap. And this is because the desorption has a different kinetics compared to the sorption. Because when the water molecule is dissolving from the bulk of the material, it's a diffusion limited process. And this will confirming with the bulk sorption dominating mechanism from the hysteresis gap as well as the uptake of the isotherm. And as you can see at the last stage of the desorption, it can still go back to 0, which means it's a reversible process. And some other kind of information you can get from this water isotherm. For example, the shape of this isotherm is a quite typical type 2 isotherm, which is widely found in the food material. And it shows a monolayer region at very beginning here, and then a multiple region for the less strongly bound water, and finally the free water region at high humidity levels. And this free water is used for the growth of bacteria, yeast, and mold that will destabilize of the material. So we can also use this water isotherm to optimize the shelf life or the stability of the food materials at certain temperature or different conditions. And the same for the water or some other organic vapor isotherms. From the classification, we can get 6 types of the isotherm. So the type 1 isotherm is typical for some microporous material, and the type 2 and type 4 isotherm are typical for the food material that the water molecule will first forming some monolayer on the surface and then forming the multiple layer on the top of the monolayer. So this type of isotherm we can use to calculate the BET surface area of the material from the monolayer region and then get the sorption constant, the BET surface area of the solid material. The other type of isotherm, for example, the type 3 and type 5 isotherm, which is typical for some condensation on the surface, that the water molecule will forming some cluster on the surface rather than cover the whole surface with the monolayer regions. So the probe molecule has weak interaction with the solid material that it will interact with itself and condensation on the surface of the material. And in case of the monolayer region, the monolayer content is considered as the most stable state, and we can use this isotherm to also predict and optimize the shelf life conditions, and also calculate it for some other kind of properties of this solid material. And another widely used equations we can calculate with the water isotherm or organic vapor isotherm is the Young and Nelson equation, which gives the constant about how much is the monolayer or the multiple layer from the full isotherm. And the other constant here is giving the degree about the interaction between the probe molecules and surface on the material. So these are some very useful parameters in the food industry for the prediction or the development of the formulations. And that's just some ideas about the step methods with the DVS system. And another kind of method we can perform with the DVS system is the ramping method, which is a much quicker and easier way to measure the stability of the material. And we can also calculate the glass transition humidity for the sample at certain temperature. And it's very similar to the DIC temperature ramp. So in case of the DVS, we will ramp the humidity from 0 to 90% RH at a constant rate, which is the blue line here. And this is an example with the lactose sample at 25 degrees. And the red line is for change of mass for the sample. So during the drying step before 500 minutes, it's losing the mass, just the flow of the carrier gas. And when we start introducing the moisture, the sample uptake is increased slowly. And here is because of the surface sorption on the lactose material. And after a certain point of humidity, the moisture uptake is increasing dramatically as the water is not only on the surface, but also go to the bulk of the material this time. So it's a bulk-dominated mechanism. And calculated from the slope before and after this point, we can then get a point for the glass transition. And from the slope, from the cross here, we can then calculate the glass transition humidity for this sample at 25 degrees. And as we keep introducing the moisture, the sample will also go through the crystallization, that the mass will drop significantly. That's because the crystalline state has smaller surface area as well as less sorption capacity. So from this single experiment, we can first get a point for the glass transition, and then we can also get a point for the crystallization for the sample. And that's the experiment we just performed at certain temperature, which is 25 degrees. We can also do a series of ramping experiments at different temperatures. At each temperature, we will have 2 points. Then we can get this stability mapping with the temperature and relative humidity. So the blue line here is for the glass transition for the sample, and the red line here is for the crystallization of the sample. With this kind of stability mapping, we can then easily predict at a certain combination of the temperature and relative humidity, is the sample at a very stable amorphous phase or a crystalline phase, or just unstable to change the structure at any time under this kind of certain conditions. So here just shows the capacity of the DVS to measure those kind of stability with the ramping method. And we do have a study here, example with the granule samples. We perform the same ramping experiment that we expose the like the coffee granule first from 0 to 90% RH during the sorption, and then with desorption from the 90% RH to 40% RH at the back. And the result here shows during the sorption step, the sample is quite stable before 60% RH here. There is no much uptake in the mass plot. But after 60% RH, there is a sharp increase. And at 90% RH here, the combination with the video camera, we took the sample images at 90%. And here's the sample image showing the sample already changed the color into a deeper color, as well as more wet compared to 60% RH state. And during the desorption, the sample mass is reaching equilibrium, the maximum at about desorption 75% RH. So the deliquescence is somewhere between 90 and 75% RH. And this is kind of stability study about the coffee granules. And we can exactly perform the same experiment on some other fruit sample as well, with the combination of the camera to take the photo images, the same time running the experiment. And then you can see a clear transformation about the morphology changes at different humidities. The previous one is the ramping method. We can get the glass transition of the sample. And with the DVS method, we can also measure the amorphous content inside the sample. And we have a very special method here. It's a method based on the vapor uptake before and after the vapor-induced crystallization. And with this method, we must need to have a kind of standard material with the known amorphous content. And we also need to find a vapor that will induce the crystallization for the sample. So with the standard material here, we find acetone solvent at 60% RH will induce the crystallization for the sample. So this is the result with the standard material. And then we perform the experiment with our sample of interest. So we first expose the sample to 30% RH here, which is for both amorphous and crystalline phase. And then we expose the sample to 85% RH to crystallize all the amorphous phase in the material. And the further exposure to 30% RH again, and this time is for the fully crystalline material. And there will be a difference between the first and the last stage here. And this is difference because of the amorphous content inside the material. And we have our standard material with a certain level of amorphous content. Then the sample material can be percentage to this amorphous content. Then we can calculate the amorphous content of this sample material, which is about 4.8% from this simple experiment. And this method is very accurate, especially for some low amorphous content material, and is quite reproducible as well. And we can detect as low as 0.2% amorphous content compared to some other traditional methods. DVS method can give a more accurate and reproducible result based on those low amorphous content materials. The next application I want to introduce here is about the packaging material. So with the DVS method, we can also measure the vapor transmission rate or the water activity with this kind of membrane or some thin film sample used as the packaging material. And we can use a very special device called paint cell like this one, which is composed of 3 parts. So we have the lid of the cell, we have the cup of the cell, and 2 rubber O-ring, which is for the sealing of the membrane. And then we can put our packaging material, which is the yellow atom here, in the middle of 2 rubber O-ring and close the cell with this lid. And we can also put some drying agent inside the cup here, which is to keep 0% RH all the time throughout the experiment. Then with the DVS system, we can change the outside concentration to different levels. So the vapor molecule will just go through the film sample from one direction only, from the top to the bottom. Then we can easily calculate the diffusion rate or the permeability with one-sided experiment. So to calculate the diffusion, we can use the Fick's law, and we have the mass at equilibrium state. We also have the thickness of this thin film sample. Then we can easily calculate the diffusion rate of this thin film sample at certain relative humidity. And we can also calculate the permeability of this thin film sample from the increasing of the linear part, the slope of this linear part. Then it will give the permeability of the material at certain humidity and temperature as well. And the case study here is about the co-sorption study we perform on some packaging material. As I introduced previously, our resolution system can generate 2 different vapors at the same time, and we can perform the sorption of 2 organic vapors or just 1 organic vapor with some background humidity. So here we have the sorption of both water and methanol, as well as the co-sorption of 2 different vapors. And this methanol molecule can represent any kind of organic vapor or even a kind of flavor molecule escaping from the packaging material. So we can set up the experiment basically with 3 different stages. The first stage is the methanol only step, that we changing the concentration of methanol to 50% partial pressure. The second stage is the water only stage, that we increasing the water concentration to 20% humidities. And the last stage is we introducing 2 different components at the same time. So 50% methanol in the presence of 20% water as the background. So we do the experiment at both 25° and 45°, and we want to calculate we want to study the effect of temperature on those molecule diffusion. So the blue line for 25 and the red line for 45. For the first stage, which is the methanol only stage, the 2 plots are very similar to each other, and also the calculated results are almost the same at 2 different temperatures. So the result here, the diffusion rate is almost the same at 2 different temperatures. That means temperature has very little effect on the methanol diffusion here. And on the second stage, which is the water only stage, you can see a difference in the mass plot, and as also the value at 45° is almost 5 times larger than 25°. That means the temperature has a very significant effect on the water diffusion. That higher humidity will changing the water molecular mobility that results in a higher diffusion for the water molecules.
Thanks everyone. Mission will be rejoining us shortly. Thank you.
Hi John, can you hear me?
Yep, you're back.
Sorry, I'm back.
That's no problem. That's no problem. Yeah, you start again. Oh, you start again.
Yeah. And I think we already talked about the water sorption only. And the last step is we have methanol with the background humidity about 20%. So this time, the diffusion rate or the permission rate for methanol molecules is about twice larger than 25°. So this means with the help of background humidity, at higher temperature, the diffusion rate for methanol is also improved as well. So this simple study just tells us about the potential of DBS to study this kind of temperature effect or the background humidity effect on the diffusion for the packaging materials. The next study, we can also use the paint cell to measure the water activity and vapor permission rate by doing a series of calibration with salt solution, the saturated salt, and then we can measure the water content in the food material, for example, honey, ketchup, or some milk powder as well. And the measured value with the DVS method is just having a very good agreement with the literature values as well. And very similarly, we can also measure the diffusion rate of some flavor molecules by putting the liquid inside the cup here and sealing with the cell with some storage bag. And then we can measure the mass loss and calculate the water flux for this certain kind of flavor molecules escaping from the storage bag or packaging material. The next application is about the heat absorption, which is a very useful parameter for the prediction of the sorption mechanism. And to calculate the heat absorption, we need to have at least 2 different temperature experiments. And the first example we have here is about the meat sample. And we perform the same experiments at both 25 and 35 degree. And we have two different samples here, which is the fresh meat and the aged meat. And aged meat is just exactly the same sample put in the fridge for a week time. And here you can see for the fresh meat sample, the plot for two different temperatures is almost the same. That temperature has very little effect on fresh meat. And in case of the aged meat, the uptake at 35 degrees is much higher than 25 degrees. That after aging, the meat has a kind of water capacity decrease at 25 degrees at lower temperature. And from the calculated result for heat absorption, that the results at 25 degrees is relatively lower than the heat absorption data is much higher for the fresh meat sample, and it's increasing with the carriages or the change of mass. And this indicates that the water molecules, the interaction between the water molecule and the meat sample is increasing. While the aged meat, the water just basically condensation on the surface. The water molecules is interacting with the water molecule itself. And that's just some parameter we can also measure with the DBS data. And we also have another case study for heat absorption. It's about the crystalline alpha lactose monohydrate that we can perform the water sorption at three different temperatures, which is 25 degrees, 35 degrees for the blue line, and the 45 degrees for the green line here. So all the three isotherms shows a very typical type 3 isotherm, where the water forms the cluster on the surface rather than the monolayer. And below about 80% RH here, there is virtually no change in the vapor sorption at three different temperatures. And above 80% RH at high humidity here, the lactose is able to absorb more water molecules at lower temperature. And this is very typical for the surface sorption mechanism. And from the heat absorption was calculated at different coverages at lower temperature, 25 to 35, and higher temperature, 35 to 45. So over the entire coverage range, the heat absorption values are higher at lower temperature, so it's higher in this column. And this value just have a very good agreement to the heat of evaporation for water at 25 degrees, which is a value about 44 kilojoule per mole. And this just indicate that the water molecule in the vapor phase are interacting mostly with the other water molecules, not on the lactose surface, just the condensation mechanism. And these results just agree with the type 3 isotherm in the previous slide for the surface absorption mechanism for the lactose sample. And the other application, we can also measure the BET surface area if the shape of the isotherm is a very good type 2 or type 4 isotherm. And the equation we use for the BET calculation just exactly the same as the volumetric technique. We measure the amount of the vapor absorbed surface and the vapor pressure above the surface. Then we can get the monolayer volume and the sorption constant. What we usually do for the BET surface area is we will perform some organic vapor sorption like octane or ethanol. Then we can get this kind of BET plot from the slope and from the intercept of this line. We can then get the BET surface area of this lactose sample, which is about 0.26 square meter per gram, with a very good linear regression. And this result for the lactose sample just have a very good agreement with literature value for the pharmaceutical grade lactose sample as well. And with DBS method, we can measure as low as 0.2 in this case, or we can also measure some porous materials with very high surface area like active carbon or silicas. And the last application I want to show here is about the formation of hydrate. That by DBS method, for example, we perform 1.5 cycles for this kind of sample, And at 40% RH here, there is a significant increase in the mass plot, which is the transformation step indicating a formation of hydrate. And during the desorption, this formation of hydrate is losing this hydration water. And at the second cycle, it can go up to the same level as the first cycle. That means it's a reversible hydrate formation. And it's very clear in the isotherm that the blue and the red line for the first cycle and the gray line for the second cycle. So the second cycle just exactly the same as the first cycle. So it's a perfectly reversible hydrate formation. And if this hydrate formation is forming at one specific humidity step, we can then use this isotherm. If we also have the molecular weight of the sample we do the measurement, we can then also calculate the stoichiometric of this water formation, like how much more of water is absorbed, is forming this kind of formation of hydrate. It's a kind of monohydrate or trihydrate from this kind of isotherm calculation. And if we perform the experiment at 2 different cycles, and this time the first cycle and the second cycle are different in this case. So this is a kind of irreversible hydrate formation that during the first cycle, the sample is already changing the structure, that the second cycle is a kind of different sample compared to the original sample for the environment. This last example, just the lactose, anhydrous lactose sample, we do the water sorption at 25 degrees. And as you can see during the last step of desorption, there is still some water trapped inside the material. It didn't go back to zero. It's a kind of irreversible process. And from the isotherm, it's also clear it's an open loop isotherm. And this kind of formation of hydrate is due to the anhydrous lactose to the monohydrate lactose, and this monohydrate cannot be removed by the flowing of the carrier gas. So these are just kind of different examples about the hydrate formation. And just in conclusion, as you can see, DVS is a very versatile and sensitive tool for the material characterization, and it can measure different parameters by choosing different organic vapors or the water molecules at different temperature and conditions. I hope you will find DVS useful in your future research, and thank you very much for your attention. Please let me know if you have any questions. Thank you.
Thank you, Mei Shen. Yes, you now have the opportunity to ask our presenter any questions you may have that arise on this topic or from that presentation. So please submit these in the questions tab or raise your hand and we can give you the opportunity to unmute your microphone and ask the question directly. Just to kick us off, Mei Shen, we have a question here. And what's the maximum amount of samples we can use for DVS measurement?
Okay. Like we have 2 different configurations for our balances. So the low mass balance is more accurate, but it can hold up to 1 gram of the sample. And we also have a high mass balance, can hold up to 5 grams of the sample. But the resolution will be a little bit higher than the compared to the low mass balance. So the maximum amount should be 5 grams of the samples.
Another question we have. They've asked, can they use water isotherm to calculate the ET surface area?
As I mentioned, it's all depending on the shape of the isotherm. So from the shape of the isotherm, the BET theory is based on the type 2 and type 4 isotherm. So as long as the water isotherm is a type 2 or type 4 isotherm, which we have the monolayer range, then we can use the water isotherm to calculate the BET surface area. But most of the cases is the water isotherm is a type 3 isotherm. So just some condensation on the surface rather than the monolayer coverages. So in this case, we need to use some organic vapors like octane or ethanol to do the isotherm, then calculate the BET surface area of the material. I'm really sorry to the break in the middle. I need to change a room in the middle here.
That's okay. Well, we don't have any more questions, so maybe we'll just we'll move on from there, Meishan.
Okay, thank you.
Thank you, Meishan. Thank you very much for putting that presentation together and taking the time to be with us today. So we'll now move on to the next speaker for today, Dr. Sebia Ahmed, the application scientist for surface measurement systems. Sebia has a master's degree in pharmaceutical chemistry at the Queen Mary University of London and a PhD in chemical engineering at Imperial College of London. After her PhD, she started working at Surface Measurement Systems as an application scientist and has extensive experience working on both our sorption systems, the DVS and the IGC SEA. So without further ado, I will now hand over to Sebia to give her presentation.
Thanks for the introduction, John. So I'm just going to share my screen with you all now. So in this presentation, I'm going to go through some technique that's a little bit different. It's regarding the IGC SEA, so the Inverse Gas Chromatography Surface Energy Analyzer. And in this presentation, I'll go through what the system looks like and what it does, and a few case studies with regards to food applications. So comparing to the analytical gas chromatography, typically in this technique, what you would have is a mixture of gas phase probe molecules, which you would then inject into a column. And depending on the interaction between the column and the probe molecules, you would obtain a separation between these probes. And as a result, at the detector, you would obtain different peaks based on different retention times. In inverse gas chromatography, however, we actually pack the column with the sample of interest, so with your sample. And in this case, we inject probe molecules individually. These are known probe molecules. So for surface energy, we typically use a mixture of polar molecules and non-polar molecules. We then inject into the column, and depending on the interaction between the probe molecules and your sample, we would obtain different peaks based on different retention times, which we can go ahead and analyze. So this is what the IGC SEA looks like. It has two drawers on either side and a drawer in the middle. When you open up each drawer, it accommodates 6 reservoirs, so we'll have 12 in total. And this is where you would put your solvents required for analysis. The carrier gas in the system is either helium or nitrogen. And when you open this door in the middle, you would open up where we would put your columns. So we have two different positions to accommodate 2 different columns. And this is surrounded by a column oven. So in this system, the column oven can go from 20 degrees to 150 degrees. We also offer a background humidity controller. So in this case, what we would do is apply background humidity on the surface of your samples and carry out the experiments. The detector is the flame ionization detector, and this is ignited using hydrogen. And this is really accurate for measuring the concentrations of organic probe molecules. So the system is quite versatile in terms of the different types of samples that we can run. So there's a few examples at the bottom. So we have carbon fiber, cotton, hair, granules, powder, and even medical implants. So to prepare a sample column, typically what we would do is how we would pack your sample of interest is a lot more simpler than the standard GC way of packing column. So we have silicized glass columns of different sizes. So we have 2, 3, 4, and 10 millimeter columns. So the 2 millimeter columns is for very fine powders. 3 millimeters for slightly larger powders. 4 millimeter columns we would typically use for maybe strips of fabric or hair or granules. And the 10 millimeter column is to accommodate much larger samples. So if you had a tablet or a block of wool or something that you would just don't really want to break into powder form, we could simply use a larger column oven. In this case, we need to accommodate, larger column. So in this case, we need to accommodate with a larger column oven. So what we do to pack a sample is insert some silicized glass wool. So this doesn't interact with any of the experiment. We'd funnel in your sample of interest and close off with some more silicized glass wool. This just ensures that there's no material going into the system during the experiment. We also have a nice YouTube clip to show how simple and straightforward it is to pack a column. So to start an experiment, the first thing you would do is pack the column with your sample of interest. We would then choose some probe molecules. So with regards to surface energy, there's two probe molecules that we need. We need non-polar solvents, and this is to understand the dispersive interactions. We also need some polar solvents, this to understand the specific interactions. We can go ahead and go to the software and choose how to inject them. So we can do very small concentrations of infinite dilution or larger concentrations. We'll then start the experiment, and depending on the interaction between the probe molecules and your sample, we'll be able to obtain different peaks at different retention times, and to analyze these, to obtain different physical-chemical properties. So in the system, we typically have a whole library of different solvents that we can use to analyze our material. So like I mentioned, a mixture between non-polar probes and polar probes. We can also include some other solvents that you wish that more representative for your sample. And in this case, we just need to fill in a few of these properties here, and we can go ahead and calibrate it onto the system. So with the IGC SEA, we have two different softwares. One is a control software. This is directly linked to the IGC SEA. And this is where you would create and start your methods and experiments. After the experiment is complete, we move on to the SEA analysis software. This is when you go ahead and analyze your peaks. And in this case, peak analysis is relatively quite straightforward. So in this case, we've injected a couple of methane injections, and this is to understand and calculate the dead volume. And in this example, we can see we've injected a few non-polar probes. So this is a resulting peak based on different retention time. And what you'd simply do is highlight the beginning and the end of the peak, click calculate, and as you can see here, all these panels will start to fill up. So calculation is automatic. However, if you did want to export the data, and use the raw data for your own calculations, that's also very simple to do. So there's a few properties that we can measure using IGC SEA. The most common is surface energy. We can also understand the acid and base interactions, and understand the Ka and Kb. We are also able to obtain sorption isotherms. And also with this information, we can calculate the BT specific surface area of your sample. We can also understand other properties such as work of adhesion and cohesion. And because we can inject multiple concentrations, we can actually obtain what's called a heterogeneity map across the surface of your sample. The surface energy is the most commonly measured property using IGC SEA. So what is surface energy? So it's analogous to the surface tension of liquids. So you're able to quantify the ability of the surface to react compared to the bulk. And in this case, we need two different probes. We need the dispersive component to understand the long-range physical interactions, and we need some Lewis acid-base components too. This to understand the chemical short-range interactions. So prior to the surface energy experiment, what we first need to know is a few different things. The first of which is the BT surface area of your sample. So like I mentioned, we can calculate this using IGC SEA, and I'll go through this in the case studies. However, if you do have this value at hand from other third-party instruments or volumetric instruments, then that could also be used. We also need to understand the molecular size of the probes. So like I said, the IGCSE has a library of different probe molecules and their physical properties. So these are the two things we need to know. So after this, what the software does is calculates the amount in moles of probe needed to achieve certain coverages across the surface of your sample. And so when we start our experiment, when these probe molecules interact with the sample, we can understand the different properties based on retention volumes at different coverages of the surface of your sample. So surface energy is an interesting property because it can be related to other properties. With increasing surface energy, you would get increasing wettability. You can also get increased work of cohesion. In this case, how likely is it that your sample material is to interact with itself? And like I mentioned before, because we can inject in multiple concentrations across the surface, we can understand any kind of defects or porosity on the surface of the sample and give us an idea of any disorder or heterogeneity occurring on the surface of the sample. We can also calculate work of adhesion. And in this case, we're looking at two unlike materials. So you have a sample material and another material. And to understand the compatibility and the interaction between these two samples. So to understand one of the things that we can do with IGCSE is to understand the BT determination. So like Misha went through the DVS, we can measure the BT surface area using the DVS technique. And this would be in the range of 1 meter squared to up to about 1400 meters squared per gram. And this is quite similar to the nitrogen absorption technique. However, the IGCSE, we can actually very effectively calculate the BT surface area of very low surface area materials, which is quite a limitation for these two other techniques. So we can go from about 0.1 meter squared per gram to 100 meters squared per gram. And this can, we can understand the BT surface area of different, a number of different other species such as drugs and minerals, excipients, and hair fibers. So the main differences between these techniques is that for nitrogen absorption technique, typically you would carry out the experiment at very low temperatures, so about 77 Kelvin. However, in both the DVS and the IGC, we can actually calculate the BT surface area based on more representative of how we would use our sample. So we can go from ambient temperatures to high temperatures. In the case of the DVS, we can go from 20 to 100 degrees, and the IGC from 20 to 150 degrees. With the nitrogen absorption technique, you are limited to using nitrogen or even krypton. However, both the DVS and the IGCSE, we can use organic vapors. And also with the nitrogen technique, we are limited to only using the experimental conditions under vacuum. And with the DVS and IGC, we can run this at ambient temperatures. With the DVS, we can also run this at vacuum as well, if necessary. So we have quite a few papers out there that actually compare our chromatographic technique with the volumetric technique. And one of the main differences that people have found is that using krypton or nitrogen absorption volumetric techniques, we see that because of the harsh conditions of under vacuum and low temperatures, you actually may be affecting and disrupting the properties of the sample material. And in this case, our systems can overcome this, and we can actually carry out the experiments at ambient temperatures and more less harsh conditions. So we don't alter any of the properties or defects on the surface of the sample. So in this example here, we're looking at understanding the isotherms and calculate BT surface area. So what we typically have here is a CRM material, and this is an aluminium material. And what we do is inject for different concentrations. So we want to stay within the BET range and at different partial pressures. So what we can do here is what we've done in this example is we've compared the volumetric technique to our technique, chromatographic technique, and we can see they're in quite good agreement with each other. So it's very comparable to the volumetric technique out there. We have also compared it to another example, CRM 171, and again, we have a very good agreement. And in this case, we're looking at the isotherm here. And with this isotherm, what we've done is applied the BET surface area and selected the linear part of the isotherm to calculate BET surface area. So again, we have a good agreement between our volumetric technique and our chromatographic technique. So one of the things I mentioned that we can do with the IGCSA is introduce relative humidity on the surface of the sample. And this may affect properties such as surface area. So in this case, we've used one of our samples and we've used octane as a probe. And in this example, we have 0% relative humidity and obtained a BET surface area about 2.9 meters squared per gram. We've then introduced an increased relative humidity to 50%. We can see a decrease in BET surface area. And when we introduce to 90%, we can see an even further decrease of BET surface area. What is this telling us? So as we increase humidity, the measured BET surface area decreases. And this is because water is now on the surface of the material. So when we introduce our octane, it's now competing for these sites on the surface of the sample. In this case, we have a quite low decrease in BET surface area. However, in cases with regards to some samples that we've seen, for example, starch samples, when we increase relative humidity, we're actually seeing an increase in surface area. And this is because of the nature of the sample. So in some cases where the sample may have a decreased availability of surface area, or some food samples such as starch, the water can actually result in some swelling. So the water can penetrate into the bulk of the material and start to swell. And this will result in an increase of BET surface area. It really depends on the nature of the sample. So in this example here, we're looking at understanding surface chemistry and surface energy of mannitol. So we're looking at D-mannitol. We also have a nice application note if you're interested. So we have two different types of D-mannitol. We have as received and silanized D-mannitol. So you want to use IGCSA to understand and characterize the surface energy compared to the contact angle. So this is the sample here, and we have different faces of the sample as well shown. So with regards to contact angle measurements, we use GIM and H2O as our probe molecules, and we've actually calculated contact angle on different facets of the crystal. And this is the resulting surface energy. So we can see we have a higher surface energy with regards to dispersive surface energy and slightly lower for our polar surface energy. We also calculate hydrophilicity by taking the specific surface energy divided by the total surface energy. So what we've done is undergone the silanization procedure of the D-mannitol. In this case, we use 5% of dichlorodimethyl in trichloroethylene for 80 degrees for 3 hours under constant reflux. So what that does is it takes the hydroxyl groups here and associates a silanization process where you have Si and Me groups on the sample. So in this case, we've calculated the surface energy, and what we can see is that we have a significant decrease of dispersive surface energy on all facets of the D-mannitol. So we've compared this to the SCA data, and what we've done here is for the surface energy experiment, we've injected different concentrations of our probe molecules to give us an indication of the overall surface energy across the surface of the sample. And in this case, we're looking at the dispersive surface energy. And these are the values here at maximum coverage, minimum coverage, and a gamma D50. So firstly, what we can understand from this is that our salinized D-mannitol has a much more lower dispersive surface energy compared to the as received D-mannitol. And in this case, what we can also see is that infinite dilution, so this region here, we have quite a higher dispersive surface energy of our as received D-mannitol compared to a salinized D-mannitol. What this is telling us is that for this D-mannitol, we actually have a few sites on the surface of the material which are high energy sites, and the probe molecules can interact with these high energy sites, and as a result lead to dispersive surface energy, high dispersive surface energy. However, when we start to salinize a sample, the salinization causes the material to be a lot more homogeneous. So these sites may be now blocked. In this case, we have a much lower dispersive surface energy. And also, this is an indication, the shape of the profile is an indication of how homogeneous or heterogeneous the surface of the sample is. So since we can interact with these high energy sites, this actually corresponds to a much more heterogeneous surface of the sample, whereas a more linear profile would be representative of a more heterogeneous, homogeneous surface of the sample. We've also calculated the specific surface energy of our material, and again the qualitative values here, quantitative values here, and we can see the same trend where we have the as received D-mannitol having a slightly higher specific surface energy, and salinized D-mannitol having lower specific surface energy. We can also compare the two as well. So dispersive compared to specific, we can see that the dispersive surface energy contributes a lot more to the total surface energy of the surface of the sample. What we can also do with this is correlate to other properties such as flowability. So due to the high surface energy of the as received D-mannitol, what we can have is correlate to higher cohesive energy and cohesive forces. So we've done an experiment where we've introduced some air velocity to the sample and calculated the total flow energy. And in this case, for the as received D-mannitol, because there's a higher surface energy can be correlated to a higher work of cohesion, these samples will actually interact stronger with themselves compared to the salinized D-mannitol. So at this low region of air velocity, we'll actually have very unstable flow behavior due to these cohesive forces. But as you increase air velocity, this is overcome by other forces, and therefore we see a kind of plateau out at higher air velocities. So the next example here, we're looking at a PT surface area of some fibers. So we're looking at some natural fibers, and there's a nice paper as well with all the specific details on this case study. So the materials here are looking at cellulose. So we have a few different cellulose samples. We have industrial fibers, and we have natural fibers. So we have a bio-made cellulose fiber, which is produced from a dry jet wet spinning process, and we also have two other fibers, the kinaf fiber and the flax fibers. And these are the corresponding SEM images that we've obtained. And you can already see that the cellulose fiber, the industrialized cellulose fiber, has been processed, and it looks a lot more finer and a lot more homogeneous compared to the natural fibers. So what we've done is calculated the VT surface area, and in this example, we've actually done a few different runs. So column to column reproducibility experiment. So what we can see here is that the experiments are very reproducible, and we have the mean is that the biomid and the kinaf fibers are quite low in VT surface area, and the flax fiber is slightly higher. And also the variation in standard deviation is quite significant too, because in our industrialized fiber, we have very low standard deviation, whereas in the other two fibers, we have slightly higher, specifically for the flax fiber. So what this is telling us is that due to the standard deviation and the higher VT surface area, we can understand that this may correlate to the surface roughness of the fibers. We've also carried out a batch-to-batch variability experiment. In this case, we've done multiple column-to-column experiments and calculated the VT surface area. So what we can see is that for our industrialized fiber, we have very small standard deviation. So again, correlating to the fact that this is a processed fiber and with a lot less deviation and a lot less heterogeneity on the surface of the sample. With these two different natural fibers, because they are natural fibers, we do have a level of heterogeneity and irregularities on the surface of the sample. And again, these irregularities and heterogeneity is because due to the fact they are natural fibers. And this is what we can see with our batch-to-batch column-to-column experiment. We've also calculated the surface energy of our material. So in this case, we've represented the surface energy in terms of distribution. So what this is telling us is that the more wider the peak, the more heterogeneous the surface of the sample. And the more narrower the peak, the more homogeneous surface of the sample. So in this plot here, we're looking at the dispersive surface energy, and here we're looking at the specific surface energy. But what you can immediately see is that our dispersive surface energy contributes a lot greater than the specific surface energy. And we can also see that the two natural blast fibers are much more heterogeneous with regards to both the dispersive and the specific surface energies. And because of the process of the wet spinning of the industrialized fiber material, we have a much more homogeneous material, and that's represented by much more smaller peak width of our peaks here. So in the next example, we're looking at surface phase transitions. In this case, we're looking at induced temperature phase transitions and understand the glass transition temperature. So we've compared this to the DSC method, which can understand the bulk TG, compared to our IGC method, which can understand the surface TG. So SEA can be used as a probe phase transition, where a change in surface properties can occur. The two ways we can understand the glass transition temperature, and this is based on phase transition induced by temperature. We can also understand glass transition temperature at different humidities, and we can also understand the polymorph transitions. So typically what we'd use for an experiment is stick to one probe molecule, so maybe decane, ethanol, or toluene, and we can measure the retention time at different temperatures or different relative humidities under infinite dilution concentrations. In this example, we're looking at alpha D maltose. So if we look at the different states of the material, if the probe molecules are able to penetrate into the surface and to the bulk of the material, and easily diffuse out, we're looking at a rubbery state of the material. However, if this is slightly restricted, and we will actually obtain a glass and rubbery material. And eventually, what we will have is just a glass material where the probe molecules can't interact with the bulk, but just interact with the surface of the material. So in this case, in alpha D maltoids, we've used decay at infinite dilution, the very small concentrations. And we can see it's going onto the onset to a glassy glass transition of the material. So we've carried this out at 15% relative humidity and 0% relative humidity. So this is the results of various experiments. So we have different levels of relative humidity from 0% to 15%, and this is the resulting TG. So as the water content, in this case based on relative humidity, as this increases, TG decreases quite sharply. This illustrates the plasticizing effect of water on the material. And the TG value measured by IGC only differs slightly from the reported DSC values. In this case, at 0% relative humidity, we have TG of 360 to 365 Kelvin. So in our next example and case study, we're looking at the comparison of different morphologies of material. So we have spray dried and freeze dried material. And just in this example, we're having a look at some SEM images where we compare the spray dried and freeze dried material of some food materials. So at the top, we have some spray dried materials, and this is commonly they commonly have more spherical particles and much smaller particle size distributions. But freeze-dried materials can come in different shapes and particle sizes, and this can influence surface energy. So in this example here, we have lactose monohydrate, spray-dried and freeze-dried. So here we have the dispersive surface energy. And we've analyzed based on the surface energy distribution. So what we can see is that for our spray-dried material, we have quite a more narrower peak width. And this is indicative of a more homogeneous sample. And the much wider peak width is correlating to a freeze-dried material. We've also analyzed based on specific surface energy. So again, we have a very narrow and sharp peak for the lactose monohydrate for the freeze-dried sample, and a much more wider peak based on the spray-dried sample is much more homogeneous based on a narrow peak, and the freeze-dried material is much more heterogeneous based on a much more wider peak. And we can also calculate the total surface energy. So this is the combination of the specific surface energy and the dispersive surface energy. And again, because the spray-dried material is much more uniform in particle shape and size, what we have is a much more homogeneous surface compared to the freeze-dried material. What we've also done is a study based on the work of adhesion with water. This is to understand the wettability of the surface of the sample. So in this case, we've injected, we have the surface coverage here, so we've injected probe molecules at different concentrations of the surface of the sample, and the work of adhesion with water here. So what you can see is that with the lactose monohydrate for the spray dried, we have a much more linear and lower wettability compared to the lactose freeze dried material. So in this case, because we have higher energy, surface energy of our freeze dried material, we will actually have a higher wettability. And this is due to the defects on the surface of the sample. So I hope this has given you an insight of what IGC-SCA is and what it can do. And I hope it's given you some insight of how we can apply this technique to various food samples. So thank you for listening, and if you have any questions, I'll be happy to answer.
Thank you, Sebia. Yes, just a reminder to our audience, we now have a live Q&A session, so please do submit any questions for Sebia in the questions tab, or just raise your hands and we can let you unmute your microphone to ask them directly. Just right off the bat, Sebia, we have a question or two here. The first one, what is the typical sample mass needed for the experiment?
So for the sample mass, what we need to do is understand the value of the BT surface area. So for typically, if you have a sample with a very high BT surface area, we need a little bit of sample, so about 10 milligrams of sample. If we have a BT surface area that's quite low, so about maybe 10 meters squared per gram, then we need more material, so about maybe from 50 to 100 milligrams of material.
Great. We have a question from Professor Langenberg, and he asks, can IGC measure the influence of shampoo or conditioner on hair?
Yes, so we have done a few case studies as well based on this example. So we have kind of virgin hair and hair which has been treated with different maybe oils or some conditioners, and we can actually compare the surface energy of the materials. And we can also inject other probe molecules. So if you're interested in maybe some specific probe molecules that may interact with the hair samples, we can also do that. But yes, it's interesting to actually compare kind of virgin hair samples with conditioned samples as virgin hair or maybe treated and UV treated hair or maybe damaged hair. They will all have different surface energy properties.
Great, thank you. A question from Alan Connolly here, and he asks, can IGC be used to predict the suitability of coating materials?
Yes, definitely. So in this case, we will do a study based on work of cohesion and adhesion. So in this case, we can understand how likely the material is to interact with itself compared to how likely the material is to interact with the coating material. And in this case, we can actually use the IGC as a formulation tool. So if we have measured the adhesion to cohesion ratio, we can actually understand which samples would be better in terms of coating based on the work of adhesion and cohesion. So yes, definitely it's something we can do with the IGC.
Thank you. Another question here. How can we pre-condition the sample before analysis?
So with the IGCA, we have in situ conditioning. So we would purge the sample with the carrier gas, so either helium or nitrogen. And so we can condition the sample just prior to any experiment. So we can condition based on a set length of time or even increasing the temperature of the sample, just to ensure that there's no adsorbates on the surface of the sample that may interact with the experiment.
Thank you. We'll just give everyone a few more minutes to submit any questions for Sebia, but while we wait, there were a few questions submitted for Professor Langenberg from earlier in the presentation, so I just thought we'd take the opportunity to give him an opportunity to address those questions. So Edgar, if you are able to unmute, we have a question here and they ask, apart from moisture, are there any concerns with regards to interaction of VOCs or gases with food?
Okay. So in our case, we are just more or less looking for water or water vapor, and probably for either propanol, methanol, acetone, and we don't have a focus on the gas interaction like CO, CO2 or whatever on the food powder, but clear there could be a a relationship or an interaction between the powder and the gas, but that's not our main focus. So we don't have a capability to check this.
Thank you, Edgar. And another question we had here, they ask, do particle size or particle size distribution also affect the temperature and humidity at which caking takes place?
So the particle size distribution, so that's normally not the big influence of the caking process. So if we have a homogeneous material, it belongs more to the humidity and to the glass transition temperature when we're running in this problem of caking. You have also, if you are focused on the mechanical caking, if you have a broad size distribution, then you have more contact area to the particles, and that could be running in some serious problem with mechanical caking.
Thank you. I can just see we've got another question coming in here, so just give me a minute. So I can't tell if this question is for you, Edgar, or for Sebia, but if whoever is able to answer it, I welcome you to have a crack. It asks, if you have a wet coating process, how will it affect the adhesion cohesion properties versus values measured of the dry materials?
So again, it's just a wet coating process, and he would like to know.
Apologies, my micro was there. The question is, if you have a wet coating process, how will it affect the adhesion cohesion properties versus values measured of the dry materials? Now, the asker has specified this was for Sebia, but if you have any insight on that, I'm sure they'd be happy to hear from you.
Okay, so I have no clue so far.
That's no problem. Sebia, would you have any insight on that? Okay, we may have lost Sebia. She's not responding, but we have run over time a little bit anyway.
I'm
so
sorry, John, I was on mute.
Oh, sorry, Sebia. Sorry, yes, so we'll take this as our last question as we are running over.
Yeah, I was.
And
Yeah,
just to remind the audience, the question is, if you have a wet coating process, how will it affect adhesion or cohesion properties versus values measured of the materials?
Sure. So if you have, if you're coating the sample, there's a few things that can happen. If the wetting of the sample causes some surface energy sites to be blocked, that can result in a decrease in surface energy, and that can cause a decrease in a work of cohesion and adhesion. However, if the wetting actually causes more swelling and different maybe interaction with the bulk of the material, then in this case we may have different levels of surface energy on surface sample, and again that can increase the surface energy and increase the work of cohesion and adhesion.
Brilliant, thank you. Now that is all the time we have for today, I'm afraid. Thank you everyone for coming and attending today, and another massive thank you to Professor Langenberg and to Hochschule Bremerhaven for working with us on coordinating and creating this online workshop. Thank you again to all of our speakers, and of course thank you to all our attendees for being here to take part in today's session. If you have any time in the coming weeks, we have a few upcoming educational events we would love to welcome you to. Our next one taking place in a few days' time on Thursday, the 13th of May, and that will be exploring the topic of BET surface area measurements by sorption methods at ambient conditions. So we invite you all to visit our website at www.surfacemeasurementsystems.com to find out more information about those events. If you have any other questions about today's webinar or workshop, and or would like to contact one of our speakers for further information, you can contact our science team at science@surfacemeasurementsystems.com. Or alternatively, if you would be interested in potentially collaborating on a future workshop or webinar, or have some questions about the presentation or the webinar itself, please contact myself at marketing@surfacemeasurementsystems.com. We thank you all again sincerely for joining us today, and wherever you are, I wish you a wonderful rest of the day. Thank you, everyone.